Dear students, welcome back. This is the MSc Electronics, paper 7, General Electronics course. The topic title is the Hartley Oscillator. The code of the topic is ELEC-OSC-S2A. This is the main component which is playing a very important role in the oscillator section. The Hartley oscillator. The Hartley oscillator design uses two inductive coils in series with a parallel capacitor to form its resonance tank circuit, producing sinusoidal oscillations. Hartley was the name of the scientist who proposed or who devised this circuitry. So normal tank circuit, if you remember in the first S1 topic, we define the oscillator as a device in which the electrical energy oscillates between the L and C. Okay, C is charged, then it is discharged through the L, and L is again expanding and collapsing magnetic field. It produces, which in turn produces the induced current, which charges again the capacitor in the alternate polarities. But the question was how to now give the feedback. The Hartley suggested that we can split this inductor into two L1 and L2, and then we can take from one of the splitted inductor a small portion of signal and feed it back to the input. So this is the main theme, you can see, principle of this oscillator, Hartley oscillator, that it uses the splitted inductor L1 and L2. The rest is the same, the tank circuit and operation is the same. So we will be discussing the key the mechanisms which are involved in it. Rest the theory you can read it out, then that is very clearly explained over here. So we go to the main circuitry. The feedback part of the LC tank circuit is taken from the center tape of the inductor coil, or even two separate coils in series which are in parallel with the variable capacitor C. So the variable with the, in some cases we may use the variable capacitor C as shown in the figure. So the Hartley oscillator is often referred as split inductance oscillator because coil is center taped. Center tape means, I have explained that in the previous classes, that in the lecture I took, that when we have a single coil, we wind a single coil starting from the let's say from this tape, and let's say we take the 500 turns. The center tape, what we do, we take a tape at the center after, let's say, 250 turns at the center of the 500, which is 250, and a connectivity is taken out. So again it split the inductor main L, total L, into two L1 and L2. So we can have a choice to utilize the two now inductors from the same one inductor, but of the half inductance obviously. So the Hartley oscillator is also referred as the split inductance oscillator because L is center tape. In fact, inductance L acts as like two separate coils in very close proximity with the current flowing through the coil. Here we will see that here the sections in the basic oscillator circuit design, we will see that the section XY induces a signal into the coil, section YZ into the coil section YZ. An Hartley oscillator circuit can be made from any configuration that uses either a single taped coil similar to an auto transformer, or a pair of the series connected coils in parallel with a single capacitor as shown below. Now this is the typical Hartley oscillator circuit design. Now if you remember, this is a common emitter amplifier. From here, if you see the self bias, this is a self bias 4 resistors here, R1, R3, this is R1, R2, these are the base potential divider resistors. R3 is the collector resistor, R4 is the emitter resistor, this is the bypass capacitor, and this is C3 capacitor, C1. These are the output capacitors. This is the input capacitor, C2. This is the transistor, that is the ground. Okay, this is the 0 volt. We can say output is taken across obviously the collector. So this is a simple self bias common emitter amplifier. So what we do, we connect at the collector. This is now the collector, you see the tank circuit, and feed back the signal to the input. Here we are from the L2 we take and feed it to the base, which requires the sustained oscillations. When this signal is fed back, what happens that it goes into the base and it amplifies, and again at the collector it is amplified, and the signal it adds to the output signal, which in the first place was going to be the dying or decaying. Now it is supplemented by this feedback oscillations. So as shown here in this that section XY induces the signal into the section coil YZ. So this is XY and this is the YZ. These are two coils we have splitted. LC tank circuit we have got. So this feedback is given into the base of the transistor. The variable capacitor is used sometime if you want to change the resonant frequency. So we can change that by changing this capacitor. It is normally not varied, but if you can have obviously variable frequencies if you want resonant frequency. The oscillator, if you want to make it a fixed oscillator of particular fixed frequency, then you don't need to that vary this capacitance. But if you have a variable oscillator like frequency generator, then you can add these variable capacitor over here in this branch of the tank circuit. So you have to explain in the exam the about all the role of the components in the circuit. This is the collector resistor which controls the collector current. Okay, and this is the base divider resistor, potential divider, which provides the necessary base biasing voltage. This is the emitter resistor which is used to the R4 is the stability of the Q point. It brings the slope of the load line down. It does not subject the load line to increase with the increase in the beta gain, as we have already discussed in the amplifier sections. The job of this parallel capacitor is to bypass, because when we connect this emitter resistor, what it does, it obviously reduces the gain at the output, because here you can see between this is the collector and this is the base. So CBE, collector to base and then emitter. So the already we have got the collector to emitter junction resistance, but we add furthermore one resistance which may cause the voltage may be divided across it. Some of the voltage drop here and the reduction in the gain may be observed. So in order to overcome this drawback, that what we do, we provide a bypass capacitor. The capacitor allows the AC current and blocks DC. So whatever the voltage which was supposed to be dropping here, it takes an easy path, which is a conducting path for the AC, and goes down to the ground and added to the output. So this is a typical oscillator circuit which consists of, this is a VCC which is providing the base biasing voltage, typical amplifier, and these are the R2, the base biasing resistors, potential divider resistors, and C3 is the output capacitor, which what it does, it takes the AC signal, it allows the AC signal and blocks the DC signal from the going out. And similarly, you see this wire is not connected over here. One thing you should know, wherever the dots are present, they are connected. Where the dot is not present, they are not connected. So it is in fact at the collector. This is, it looks like it is connected at the base, but it is not like that. It is connected at the output circuit. The tank circuit is connected. So again, C1 is there to allow the AC oscillations inside. And when we can have the, when the capacitor and L and C oscillations are started over there, again the DC oscillations are being provided from here. Sorry, the DC voltage is being provided, DC base biasing voltage from VCC. So that's a typical Hartley oscillator circuit. The rest you can read it out. Basic principle we are going to discuss. So the frequency, or the resonant frequency, is given by equal to 1 over 2 pi under root LT, the total inductance times C, where LT is the sum of the L1 plus L2 and plus 2M, the mutual inductance. So note that the LT is the total cumulative coupled inductance if the two separate coils are used, including their mutual inductance. If there are coils which are like the transformer, two coils are there, then this additional mutual inductance has to be included. But if it is a single coil, then there is no need of this 2N, only L1 plus L2 will be used. The frequency of oscillation can be adjusted by varying the tuning the capacitor, as mentioned at C, or by varying the position of the iron core, iron dust core in the inside the coil. Two ways we can adjust the, because resonant frequency depend upon the L and C. So either change L, change F, change C, change F. So either of these two parameters, if we change, we can change the resonant frequency, or desired frequency can be achieved. So that is the inside the position of the iron core inside the coil, and that is inductive tuning. That is termed as inductive tuning. But if we change the C, that is called the capacitive tuning. So giving an output over a wide range of frequencies, making it easy to tune. The also Hartley oscillator produces an output amplitude which is constant over the entire frequency range. As well as the series fed oscillator above, the above one is called a series feedback or feedback oscillator, because the path is connected in series with the base. So over there, it is possible to connect the tune tanks and circuit across amplifier as a shunt fed oscillator. So we have two the types of these circuitries. We can have series feedback and the shunt feedback. We have discussed these circuitries in the previous topics. This is the shunt feedback shunt fed Hartley oscillator. In this case, you can see that it is now directly given at the base from the output. This is RFC coil, radio frequency coil, which is job of the coil is to allow DC and block AC. So VCC, this is the VCC is released for the biasing, and this is a very simple typical. It could be a self bias oscillator, but a self bias amplifier. But in this case, we are just simply giving the illustration of a simple shunt feedback. So here we have a capacitor C2, and it is now connected to the base. The another capacitor we can call it. This is a C, which is the LC tank circuit. Feedback is now being parallel. It is shunt, we call it, directly to the base. From the we are taking parallel from the output and to the input. It's a shunt feedback. Shunt means parallel feedback. So in the shunt feedback Hartley oscillator circuit, both AC and DC components of the collector current have separate paths around the circuit. Since the DC component is blocked, by the capacitor C2. C2, no DC flows through the inductive coil, and we have the coil L, and less power is wasted in the tuned circuit. So that is one of the advantages, that the power loss is controlled in this case. Then we have the job of the radio frequency coil in the RF choke, we normally call RF choke, which has high reactance at the frequency of oscillation, so that the most of the RF current is applied to the LC tuning tank circuit via the capacitor C2. So the DC component passes through the L2 to the power supply. So DC component passes here through the we have the L2, okay, here, as I already mentioned, to supply the power, as the resistor would be used in place of the RFC coil L2, but the efficiency would be less in case of the resistor. Now Hartley oscillator gave a very simple numerical example. The example number 1, the Hartley oscillator circuit having two individual inductors 0.5 millihenry are designed to resonate in parallel with a variable capacitor that can be adjusted 100 picofarad to 500 picofarad. Determine the upper and lower frequencies of the oscillation, and also Hartley oscillator's bandwidth. So we have the two splitted coils are 0.5 millihenry each, so and 0.5 L1 and L2, 0.5 millihenry plus 0.5 millihenry is equal to 1 millihenry. Hartley oscillator, now the upper frequency, when we take, obviously with the first C1 we take, L1 C1 we put over here, so upper frequency is 100 picofarad. So if you put these value 1 millihenry, then we get the about 50, how much is this, 503 kilohertz, 503.22 kilohertz. Okay, so 503 point or we can say that 0.5 megahertz. The upper frequency is 503 kilohertz. Oscillator lower frequency, similarly we put the lower the range of the capacitance, and we get the 225 kilohertz. So what we have, the bandwidth is the difference of the two. We have the FH minus FL. What we get, 503 minus 225, this must be kilohertz, obviously, 278 kilohertz. So this is the typical example for the solving the numerical problem. Now our Hartley oscillator can be made from the operation amplifier. We will be also discussing the operation amplifier, but we are taking these first, these two basic analog the devices. As we have, as well as using we be using the bipolar junction transistor as the amplifier, active stage Hartley amplifier oscillator. We can also use either field effect, any kind of these devices, transistors can be used, FET like field effect transistor, or an operation amplifier. We will be doing that FET later, but by the time you might have that FET and op-amp might be uploaded, you might have studied that, then it will be easier for you. So an operation amplifier, this is not in your course for the Hartley oscillator, but only that the bipolar junction transistor is included. So just for you, the sake of knowledge, you must also should have the idea about it. Op-amp means operation amplifier. The operation amplifier, an op-amp Hartley oscillator is exactly the same as for the transistorized version, with the frequency oscillations calculated in the same manner. Consider the circuit below. The Hartley oscillator op-amp circuit. This is a typical Hartley oscillator. Let me show you the IC version. This is the op-amp amplifier IC 741. Now it has these pins, and this is the typical diagram for that. This is the, and at the moment what we are using in Hartley, these are the two, the non-inverting input and inverting input here, and the one output, which is the 6. Rest of the biasing is done inside, which is the VCC with negative power supply. Those circuits are not shown over here, which is making this the amplifier working through this biasing, which is the VCC plus VCC supply, and the offset values input and the two input offset terminals 1 and 5. So in this case, what we are using, this is a plus and minus. At the, we have the LC here, L1 and L2, again that the same similar, they are connected together. L1 is connected in series with the L2, and feedback is being given through the L2 again, and the oscillations are set up between the L and C, L1 and C, and you can see here the feedback through the L2 is given, injected into the tank, and sustained oscillations at the output are obtained. So this is the forward, the signal which is being passed on to the output. So the advantage of the constructing an Hartley oscillator using an op-amp is at its active stage is that the gain of the op-amp can be very easily adjusted using the feedback resistor R1 and R2. So these are two resistors, R1 and R2. As with the transistorized oscillator above, the gain of the circuit must be equal to or slightly greater than the ratio of the L1 by L2. I think it's a 2 only, but it is slightly equal to or slightly greater than the ratio of L1 to L2. If the two inductors inductive coils are wound onto a common core, the mutual inductance M exists, then the ratio becomes L1 plus M divided by L2 plus M. With this we reach to the end of the topic. Rest is the summary. You go through, read it out, and have an idea about it. So I hope that you will have a better understanding now of this topic. Okay, thank you.